Okay, I think it's the time to start. So I welcome you to the course CML 726 once again. And so do you see the recording? It has already been started. Do you see my screen?
Yes, sir.
Anyone? Okay,
Yes, sir.
great. So let's start with this course contents again. So last class we have decided that we have two parts. The first part I'll be teaching after the minor, and then Professor Hemant Kashyap will be teaching the next one. And just a minute. Okay, so today I'll be covering a small part of this first part, which is on thermodynamics and statistical. Today I'll be covering the thermodynamics part. So, and then we will learn something about the statistical thermodynamics. We'll mostly revise all the concepts that we have already studied. Then from there, once we cover these two topics, major topics, then we'll move to some practical aspects, like we'll build a molecule. From there, we'll do some quantum calculations, optimization, and then we'll set up a simulation, like a tutorial kind of thing. Okay. So we'll have very small hands-on session, very short one, but mostly it will be theoretical. And okay, let's see how it goes. Okay. Now, introduction to thermodynamics. I have kind of assigned two classes. Today I'll be covering mostly the thermodynamic laws, entropy, free energy. So we'll mostly revise or kind of recap all the things that we have studied in undergrad and postgrad. And then the next class, I will try to cover few things related to phase transitions, phase diagram, because those are relevant for this course. And it will be useful for your, let's say, whatever you do in your next step. So before switching to the, and then statistical thermodynamics we will cover in the later stage. Okay. So today, the first one, thermodynamics. Before starting the course, may I ask something to you all? How many of you are from chemistry background? Can you raise your hands? Just to get an idea, okay? Accordingly, I need to tweak the slides or the course material, because we have a kind of heterogeneous class. Okay. And anyone from physics? Okay. And I guess materials and biology, anyone is here? Okay, so I got an idea about the thing. Okay, great. So that's fine. So it will help me to design the course content accordingly. So I will try to make a generalized one so that everyone can kind of get the concepts, and then from there we'll start few advanced topics, and then let's see, we try to cover the main parts. So let's start with the thermodynamics. So most of the things probably you have already studied. So consider this class as, you know, kind of revising all those or kind of recalling all those ideas. So in this slide, I have put one schematic. So you see if you think of particles, okay, very tiny ones, subatomic particles. So you can think of electrons and nuclei, right? From there, you scale it up and then you go to atoms, and then you kind of add those atoms to form molecules, and then you can take a kind of an ensemble of molecules like 10, 15, 100, 10,000, 1 billion, okay, and then you can form a kind of a state that we can call as microstate. And then when you remove the descriptions of atoms and molecules and think the system as if it's a bulk system, then you can call them as a macro state or a state, thermodynamic state. So how do we describe or how do we study this different, let's say, type of systems? So if you want to study the electrons and nuclei or subatomic particles, then you have to take the help of quantum mechanics. Then when you want to study atoms or molecules, you have to switch to statistical mechanics or statistical thermodynamics, where you deal with these molecules, atoms, and microstates, and how do they behave. And from there, you can understand the thermodynamic state. So you switch to the classical thermodynamics. So the physical chemistry can be divided into three major parts. Okay, here I'm not listing the other parts like spectroscopy and all, but mostly quantum mechanics, statistical mechanics, and then classical thermodynamics or normally thermodynamics. And then there is another one, it's called kinetics, where you talk about rates, like the reaction rate or the, let's say, any physical chemical process. It can be nucleation rate, crystallization rate, or chemical reaction. Okay. So this is the overall, uh, the major topics in physical chemistry. Now, let me start with a simple system. So you think of a glass of water, which is shown here. And from there, if you want to see what is happening, I mean, at a first look, when you see a glass of water, you think, okay, this water is at normal temperature and pressure. It's inside a container, and that's it, right? You don't see anything other than that. Of course, if it is clear, it says pure water. Then, if you want to visualize what is happening inside, so you have to zoom in. And in order to do that, of course, there are many spectroscopic techniques or experimental techniques. But then there is another one, we call it computational microscope or computer microscope. So in that, if you want to study this, if you want to visualize what is happening inside water, you do some kind of molecular modeling or molecular dynamic simulations. So again, molecular modeling is essentially you model the system, real system, and try to mimic what is happening inside. So here I show you one movie. So we tried to zoom in. So we took a small portion of the water and try to understand what is happening inside. Now, before showing the movie, I want to ask you one question. Can any one of you tell me how many water molecules are there inside, let's say, one glass of water or one bottle of water? Anyone? How many molecules? Can anyone guess?
So with the amount of water, we can guess the number of moles, and accordingly we can calculate the number of molecules.
Yes. So can you tell me a number?
If you could tell me the
10 to the
weight
power
of that.
22.
10 to the power 22. And who tell this answer?
Sanchi, sir.
Okay, great. So thanks to both of you. Yes, you're right. So 10 to the power 22. Why not 10 to the 23?
So that
Okay.
is for 22.4 liters.
Yes, correct. So yes, in the order of Avogadro number. Okay, and then of course, if you really want to know the exact amount, then you have to do a little bit of calculation. But it has Avogadro number of water molecules. Okay, that's great. So then we want to see what is happening to all these water molecules. What we did, then we did a molecular dynamics simulation. Here is the movie. So inside water, you see water molecules, they're moving around and interacting with each other. You might see some dotted lines. Do you see those? Those are hydrogen bonds, let's say. So the water molecules, they form and break the hydrogen bonds and they interact with each other. And that's why water is liquid and we can drink it. So starting from quantum mechanics or quantum mechanical descriptions and using taking the help of statistical mechanics and little bit of programming, you can really do this. You can really model what is happening inside real water, and you can do all sorts of analysis. From here, you can calculate the, let's say, viscosity and what else, diffusivity, and then let's say the heat capacity. Okay, so all sorts of things you can calculate, and from there you can analyze at a given temperature and pressure what are the properties of water. Okay, now so this is pure water, and then if I tell you there is something else, I mean there is something more interesting than that. If you focus on the right side top movie, this one, so this is carbon dioxide, this is a carbon dioxide system, and it do you see any change? Do you notice any change? Anyone? Please switch on your audio and just say something.
Symmetric stretching.
There
Okay.
is some ordering.
There is some ordering, and somebody said symmetric and asymmetric stretching. Anyone else? Okay, good. So both answers are correct. So okay, symmetric stretching and all they are happening, of course, but the main part which I want to emphasize is the fact that you see there is some kind of ordering. Okay, so the molecules were randomly placed, and then slowly it switches to an ordered state. And I think most of you, or I think everyone knows dry ice, right? So do you know the latest use of dry ice in the COVID scenario? Anyone? There is a huge demand of dry ice to store
to vaccine storage.
Exactly, yes. So the dry ice is very important for us, and so this structure, whatever you are seeing, the ordered state is a dry ice, carbon dioxide. So we started from a fluid structure, or let's say liquid CO2, and then we carried out some molecular dynamic simulation, and we could study the phase transition. So this is called first order phase transition. Then the bottom one, the right side bottom one, there is an enzyme. Okay, this is a protein which is part of the metabolic pathway of Plasmodium falciparum, which is the positive agent parasite for the malaria. And if you can kind of understand the mechanism of this enzyme, and if you can block this enzyme, then essentially you kill the parasite. So you stop the metabolic pathway, and that's how you can cure malaria. Okay, so you can design a drug molecule that can inhibit this enzyme, and then eventually that can help in combating malaria. So again, this is another molecular dynamic simulation trajectory or movie where you see some kind of changes, like some flexible loops are opening, and those asterisk marks are the active site where the reactions take place. Okay, so all sorts of things, or this kind of movies you can generate, or this kind of analysis understanding you can have, starting from quantum mechanics to classical thermodynamics. So I hope this kind of gives you an idea about the whole physical chemistry, or at least molecular modeling part of physical chemistry. Now I will switch to, let's go back to the textbook and try to understand or revise the thermodynamic concept. Anyone has any question, query? Okay, so I want everyone to be involved and engaged in this class. And these online classes are usually bit difficult because I'm talking to the monitor. I don't see your face, and you guys also probably are having the same experience. So, but just in order to make it more lively and engaging, try to say something, okay? Try to ask something, let's say discuss something. And if I ask some question, try to say something, whether it's wrong, right? I won't judge you. I won't kind of tell you anything. But let's just make it more lively. That way we'll kind of we'll do better. Okay. So in thermodynamics, I think everyone studied this in undergrad. So the first thing we talk in thermodynamics is a system. Okay, so system is a small part that we choose. It can be anything. Let's say in a non-COVID situation, if I would take the class inside a classroom, then you can think the classroom as a system. Okay, and then the outside of the classroom, okay, is called surroundings. And then beyond that, or even if you sum them up, system and surrounding, then you have the universe. So universe is universal. So there is no limit. So the system that we are mostly interested in, surroundings that the system interacts with, and then the universe. So system plus surrounding is the universe. Then now if we focus on the system, what kind of systems we can think of? So the first one is called isolated system. So probably the meaning of this word isolated is sufficient to anticipate what kind of system it would be. Usually an isolated system is surrounded by kind of a wall that will not allow the exchange of mass and energy with its surroundings. Do you see my mouse cursor? Anyone?
Yes, sir. Yes, sir.
Yes,
We can see.
Okay, great, thanks. So here I have drawn a square, so you can think of it as a system which is surrounded by a wall which does not allow mass and energy to be exchanged with the surrounding. So this is called isolated system. Then the next one is a closed system. So closed system, it has a wall, but this time mass is fixed. Okay, but energy can be exchanged with its surrounding. So the first one, both are not allowed. The second one, mass is fixed, but energy can be exchanged. Then the third one, it's called open system. So in this case, both mass and the energy can be exchanged with its surroundings. So you can think the walls as permeable wall. So the particles can come out of the system, and the particles in the surrounding, they can enter. Now let me give you an example. So I think most of you had coffee or tea during your breakfast. So let's try to correlate something with your experience. Okay, I hope everyone knows these pictures. So in the morning, you had your coffee. Okay, if you keep your coffee in a thermo flask, what do you think? It stays there. Okay, so you don't need to worry about the amount of coffee. It will not be dissipated outside, and it will be warm, because the thermoflask has the walls which are insulator. That does not allow the heat to be transmitted or dissipated to the surrounding. So this you can imagine as an isolated system. But of course, if you tell me that, okay, sir, after 6 hours or 7 hours, eventually it will cool down. But those are like I'm telling an ideal case. Okay, so this is an isolated system. Then, if you have your coffee in a cup and you cover it with a lid, then there is a chance that the heat can be dissipated outside. So quickly your coffee may get cold. So this is called closed system, but you are still safe. You are still happy because the amount of coffee is not decreasing. Okay. Then you have open system, but then don't get scared. Here also your coffee content will be same, but the water molecules, you see, as the vapor is coming out, so the water molecules, few of the water molecules will evaporate. So this is called open system. So it can exchange particles and energy with the surrounding. Okay. Now, again, coming back to the glass of water, if you think of the properties of the system, so you can have two types. One is extensive properties or extensive variables, if you say in a different term. The extensive variables, they do depend on the amount of the substance present in the system. Let's say volume, heat capacity, internal energy, enthalpy, entropy, and free energy. So these are the properties that depend on the amount of material or amount of substance present in the system. And then you have intensive properties. Those are, so intensive, you remember intensive, you can take the first IN and you can correlate with independent. So intensive, independent. So it's independent of the amount of substance present in the system, and it's like temperature, molar volume, and molar specific heat, and all molar thermodynamic properties are intensive variables. Okay, but remember, intensive, independent. Okay, and then you'll not forget it. Now, what is the state of a system? The state of a system can be defined based on these four variables: pressure, volume, temperature, and number of particles. Now, for a closed system, closed or isolated system, number of particles is fixed. So, out of the three variables, pressure, temperature, and volume, you can take any two of them to describe the state of a system. So you can take pressure and temperature, temperature, volume, pressure and volume. Okay, so if you take two, and the other will be constant, and n is anyway constant for closed and isolated system. Now there are several thermodynamic processes. Okay, and I'm not going to tell in detail about those processes. You can read Atkins Physical Chemistry or any physical chemistry books. These processes are like reversible process, irreversible process, isothermal process, isochoric, adiabatic, and all. And there are many equations, many relationship. You can have a look, but those are not so useful in this particular course. But anyway, it's good to know those things. Okay, in interviews or in your other platforms, you might need those. Now, let's switch to thermodynamic laws. I mean, every one of you know about this thermodynamic laws. The first law, it talks about conservation of energy. The second law instead describes or gives us an idea whether a particular process is feasible or if it is spontaneous. While the third law, it kind of evaluates it. Using the third law, we can evaluate the thermodynamic properties and we can get an idea about entropy at absolute zero temperature. And there is another one called zeroth law, which gives the concept of temperature. Okay, so let's discuss the first law very briefly. Okay, I will not derive any of those equations, but just the concept. So the first law, as I told you, it's a law of conservation of energy. So what does it mean? So this means the energy can neither be created nor be destroyed. It can only be transformed from one form to the other. I think probably it's more than 20 times that you have heard this statement starting from your school days. Okay, so let's see what in the context of thermodynamics, what does it mean by this law of conservation of energy? Now you can think of a system. Let's say this is a kind of a gas chamber, and you put 1 mole of gas, ideal gas, and then on top you put a piston which is weightless, frictionless. Okay, it's kind of hypothetical one, and we have the constant pressure. That's a 1 atmosphere, the normal one. Then you apply heat. If you apply heat, then the gas expands. So it expands from volume V1 to V2. So then you get some work. So there is a conversion between heat and work. Okay, this is the conversion that we're talking about as the transformation of energy. So heat can be converted to work. Now, so we can write an important equation, which is the Q, which is the heat plus the work, is equal to delta U. Now, U is the internal energy. So what do you mean by internal energy? Anyone?
It is dependent on temperature.
Okay, but what is it? Why is it called internal, and why is it? Okay, so what is there in the name?
Total energy
So
of
the
system.
energy arising within the system
Okay.
due to the movement of molecules or the particles present within the system.
Okay. Yes, and anyone else?
Amount of energy holded
So
by
it
a
is the
particle.
total energy by. So it is the total energy by virtue of every work or change in temperature or anything that is happening inside the system. The total energy consisting of those changes.
Okay, perfect. I'll take another one.
We can say it comes from the internal degrees of freedom.
Okay, perfect. You see, I wanted to take many, let's say, answers, because that will give you an idea about your concept, and it will expand your, let's say, thought process. So we got like 3 answers, all are correct, but you kind of think in 3 different, or 3, 4, 5 different directions. So the internal energy is the energy which is there because of the existence of the system. And then if you zoom in, somebody told me that there are molecules, they interact with each other. Somebody told me that it depends on temperature, and the particles move around, and there are molecules, they have different type of modes, they can interact with each other, or the bond vibration, everything. Literally the total energy, which is the reason for the existence of the system, is the internal energy. Okay, so then we can write the expression of work. So what is work here? Work is defined as the product of P and delta V. So it's called PV work, or mechanical work. So what do we mean by that? We have a pressure which we call as external pressure, and then we have a change in volume. Okay, the V initial and V final. So the work is equal to minus V external into delta V. Okay. Now, if you kind of do a reversible process, okay, reversible process means you do very infinitesimal change. Then you can write the work, the expression of work. Yes, and as I told you, we have ideal gas in the system, so we can use PV equal to nRT, and from there we can write the expression of work as minus nRT ln Vf by Vi. Now, if you want to, let's say, draw a very well-known or popular diagram, which is called PV diagram. then it looks like this. So on y-axis you have pressure and the x-axis you have volume. And this is called PV isotherm. Why is it called isotherm? Anyone?
Temperature is
The
constant.
temperature means constant.
Okay, great. So temperature is constant. So many a times, probably in your, let's say you guys are doing masters and many of them have already enrolled for PhD. You guys might expect or have already got this question during interviews. Many questions are there from this PV isotherm. So they start, usually we start or we ask the students to draw the PV diagram, and from there we really kind of ask details about what is there, what is y-axis, x-axis, and what if you have the pressure constant. So can you identify the area where the work can be evaluated when the pressure is constant? Okay, so just have a look at the PV isotherm or the PV diagrams in your any of the physical chemistry textbook and try to understand all sorts of things. Okay, just take the diagram and read what is happening if we increase the pressure, if we decrease the volume, if we increase the temperature, if we decrease the temperature, what would happen? So this kind of, you do like a very detailed study of this PV isotherm. It's very fascinating to understand. Okay. Now I go to the next one, second law of thermodynamics, which talks about the feasibility or the spontaneity of a process. So very vague, or I shouldn't say vague, very one of the simplest possible definition of second law would be heat flows from higher temperature to lower temperature. So every one of us has experienced this, right? And I think that even any kid can say that heat flows from higher temperature to lower temperature. This is the base of the second law of thermodynamics. And of course, there are many definitions like the Clausian statement, the Planck's Kelvin statement. Okay, you can read all of this in your textbook. But here I want to tell you the concept. What do you mean by second law of thermodynamics? What do you mean by feasibility? So let's say if we have two systems, A and B, and if the temperature difference between these two systems is not equal, then there is a chance that heat can be flowed from one system to the other. So this is called feasibility. So that means there is a probability of heat flow. Then somebody can ask which direction heat would flow. Again, we know it from high temperature to low temperature. Then how long it will flow? So the heat will flow until when the temperature temperature of the two system becomes equal. So it gives feasibility, it gives direction, it gives spontaneity. Okay. Now the next thing, the implication of the second law of thermodynamics is the concept of entropy, and it's one of the most wonderful thing that happened or that people derived. So the concept of entropy. So what do we mean by the word entropy? So if you can kind of divide entropy into two terms. So first one is N, which means in, and the second one is tropy, means transformation. So entropy means this is a quantity or this is a variable which causes some transformation. So can any one of you tell me any process or any experience in your daily life where you can correlate entropy? Anyone? Have you seen entropy, or let's say a process where you can think of entropy? Anyone quickly?
So like if a metal object is placed in sunshine, then it heats up. So
Okay.
that heating up
Okay.
is.
And if I tell you entropy is a chaos, it's a definition of a chaos. Do you see any chaotic process happening around, like in your daily life, or have you seen any chaotic process?
Disrupting a line of ants.
Disrupting
So
a line.
usually when
ants.
So usually when a lot of people exit a particular room or, for example, movie theater. So initially there was an order.
Okay, perfect. Great. So let's say, okay, now the all theaters are closed. So let's come back to some example. Again, I cannot take the example
Young
of a
students
class.
and a student in their childhood and a student in college life.
That's a good one, but it has time. So we have to deal with kinetics. Okay, time dependent. Anyway, so let's say again the classroom example. Of course, the COVID does not allow us to sit in the classroom, but if you think of a classroom when you are being taught, then you are sitting inside a classroom, and then once the class is over, then you slowly or like you really rush or slowly. It depends on again the childhood or college days. But this is a process. It's a spontaneous process. Okay. So after the end of the class, people will move out, and then the entropy increases. Okay. So this is a process which can be studied or which can be realized based on second law of thermodynamics. Now, a definition of this entropy change, okay, can be related with the heat. Now, if you think of a material, okay, or any system which you heat up, so I think who said this? Deepika, right? Anyway, so if you apply heat to a system, then you essentially increase the chaos. You essentially increase or you distribute this energy inside the system. So if you think of a molecular system, it will be distributed on the molecules. And eventually, then the chaos in the system will increase. Okay, so that's why the entropy change is defined as Q reversible by T. Now, if you have a close look at this equation, delta S, again I wrote it in a macroscopic state, delta S is inversely proportional with temperature. So that means entropy change decreases when you increase temperature. Okay, and do you think any kind of paradoxical thing here, or can you understand it? We know that as we increase temperature, entropy increases. But there is a little twist here. Entropy change decreases when we increase temperature. Anyone?
Sir, entropy increases due to increase in temperature, but this one is a change in entropy. So
yes.
With a successive change in temperature, the entropy change will keep on decreasing at high temperature.
Okay. Yes, great. So thanks. Actually, I'm not able to. So I'm not able to see your name, but so that's why I'm not able to call your name. But anyway, thank you, because I'm seeing only my monitor and the slide. Okay, so anyway, pardon me for that, but thank you. And the author of the book, Peter Atkins, he has a very unique example, and he says that if you sitting inside the classroom and then somebody sneeze, okay, so the classroom is at, let's say, low temperature because everyone is in order state. So you can think of it as a lower temperature case. If you sneeze, then you suddenly see there is a chaos. Everybody will look at each other. In COVID times, it will be a disaster. Okay. Then, but if you go outside like this Chandni Chowk market or somewhere, if you sneeze, then probably there will be little change because there is already huge chaos. So you can correlate this with this, okay? So already there is a chaos at high temperature, and then if you increase a little bit more temperature, then the entropy change will be very less because the energy states are already populated. So these, again, it will be clear during your statistical thermodynamics part. Okay, we'll come back to this part. But anyway, you got the concept, right? Then let me quickly move to the free energy, which is one of the important part of thermodynamics and, of course, molecular modeling, molecular dynamics simulations. This quantity will be really useful, and we'll discuss more in detail in later part of the course. So the free energy, as all of you know, there are two free energies. One is called Helmholtz free energy, and another is called Gibbs free energy. The Helmholtz free energy is either people write F or A, which is defined as enthalpy minus Ts. temperature and entropy. But the Gibbs free energy, which is a function of temperature and pressure, can be written as G equal to internal energy minus temperature and entropy. And there is a famous equation, Gibbs-Helmholtz equation. This is the simplest form, and there are of course other forms you can look at. So this is again important because it gives an idea about the relationship between delta G, the free energy change, enthalpy change, and entropy change. So literally you have everything in this equation, and this equation is very, very important for practical applications and for theoretical understanding, for your interviews, and for your life. Okay. And why did I say for your life? That you'll get to know by the end of this class. Now, coming back to, let's say, lab experiment, where you can think of a chemical reaction which goes from reactant to product, and you can have two scenarios. In one, it goes from reactant to product, and the product state is less stable than the reactant. So there is delta G, which is greater than 0. Again, the delta G is the difference between the reactant state and the product state. And then there is another scenario right hand side where the product is more stable. So delta G is negative. Yes. So the first case where delta G equal to positive, we say that the reaction is not spontaneous. And where in the right side case where delta G equal to negative, then we say that the reaction is spontaneous. Of course, there are many other like parameters that we have to take care of. But this is a simple description, a demonstration. The first one is called endergonic reaction, and the second one is called exergonic reactions. And when you don't talk about entropy, then you have internal energy, and you talk about endothermic reaction, exothermic reactions. Okay, and have a look at these kind of discussions in any physical chemistry book. Okay, then I have a few minutes. Again, so let's say, let's move to third law. Third law gives us an idea how to evaluate thermodynamic properties. The first statement or theorem was given by Nernst. So it's called Nernst heat theorem or Nernst statement. He said that for any isothermal process of a pure component system, entropy change is equal to 0 at when we reach to the absolute 0 temperature. There are many, let's say, debates on this particular statement, but this is a simple definition of the third law. And there's another one by Planck. He said the entropy of a solid, perfectly crystalline solid, or a liquid, you have to be really careful, okay, when you talk about liquid and entropy. But for a perfectly crystalline solid, the entropy at absolute 0 temperature is 0. Okay, this is true to a certain extent, and there are exceptions that we'll discuss in the statistical thermodynamic part. But this kind of gives us an idea what happens near absolute 0 Kelvin temperature. You can read more about this, okay, in your free time. And then there is another law, which is called zeroth law, which says that if two systems that are in thermal equilibrium with each other, with a third system, then both of them will be in thermal equilibrium with each other. So that means if A is in thermal equilibrium with B, B is in thermal equilibrium with C, then A and C should also be in thermal equilibrium with each other. And this gives us an important property which we call as temperature, which is common to all these three systems. Now, there is something fun, okay? So I just wanted to make you your life more comfortable. So thermodynamics is boring, or whatever theoretical if you think it's boring. If few of you find it exciting, then yes, exciting. For me, it's very exciting. It will probably enhance your excitement or understanding about thermodynamics if you watch this beautiful, one of the best TED Talks I've ever watched. It's by Peter Atkins, again the writer of the book Physical Chemistry. You should get nervous. Okay, and it's on the second law Of course, it's on thermodynamics, but he mostly emphasized on second law of thermodynamics, and he gave a very, very interesting title, the second law, why worse can be better. It's a 15 minutes video, but watch it in weekend, in free time. Then you will understand something more about thermodynamics, life, and how they correlate. And I'm sure you'll not regret investing your 15 minutes time. Okay, so let's stop here for today, and then we'll discuss about the fluid, the phase equilibria in our next class. And so for today, that's it. Okay. So now, if you have any question, we have 3 minutes left. So please, you can ask. Okay.
Excuse me, sir.
Yeah.
Sir, I just had a thought. Like you said, entropy is related to change in heat. It is directly proportional to heat. But if I have a system containing gas particles and I simply increase the volume, so obviously the gas particles will be spread out in that extra volume too. So even if I don't provide it heat, so won't the entropy increase with the increase in volume?
Yes, of course. Again, so that's why we have these processes called isothermal, isochoric, isobaric. When you have, let's say, if you expand the gas at a given temperature, so temperature is fixed here, then you increase the volume. Okay, then of course the entropy will change, and the relationship of entropy, volume, and temperature, if you can look at it in the Atkins book, then in the next class I can tell you. But of course,
Excuse me, sir.
will change.
Excuse me, sir.
Yes.
Just to answer the question that Pooja has put up, can we think it in a way that when we increase the volume, the gaseous molecules will start moving, and due to which the kinetic energy will increase, hence increasing the internal energy?
Okay. Yes, this is another description. I can tell you more about this based on statistical thermodynamics. So if you expand the gas, okay, so the molecules are, of course, you have to check whether there is any phase transition. But if you just expand the gas, then if you think of statistical thermodynamics way, then the many energy states will be populated. So you will have many configurations. So if you think of water vapor, then as you increase the volume, then there will be many configurations. So if you think entropy, the definition S equal to K ln W. So number of, in terms of probability distribution, it will increase. So eventually it will increase the entropy. So there are many sides of concepts that you can explain this process.
Can be related to the first law, that change in heat is directly related to the work done. That delta Q that is equal to work done is change in internal energy. So if we expand some system, or if we change volume of a system, then some work will be there will be some change in heat. So that means there will be change in entropy from the first law of thermodynamics.
Yes, sure.
Sir, like you said, internal energy is because of the existence of the system. So can there be no mass without energy? Can there be any mass without energy?
Can there be any mass without energy? Do you think so? Can you tell me an example? Any, let's say, one atom, there are something happening inside, right? If let's say if you think of a molecule, then there are this vibrational, let's say if you think of water, the oxygen interacts with hydrogen, and then if you just focus on only one atom, inside one atom there are something happening. If you go subatomic level, electrons, nuclei, So can you think of something?
Sir, I was thinking about the condition at absolute zero, because people say when there is no energy left.
So in absolute zero temperature, then the internal energy, so you are essentially kind of freeze the system. Okay, but we cannot say exactly if the internal energy equal to 0. Maybe, but this is again absolute zero temperature is like a, it's not achievable, but many things, many mysterious things happen. So I'm not sure if it is exactly 0 at that.
Thank you, sir.
Okay, so I think now we have crossed the time, so 52. If you have any other class, or if you don't have, you can ask questions, or if you have other class, then we can wrap it up. Then we start discussing about phase equilibrium next class. Okay.
Thank you, sir.
Okay.
Thank you,
so
sir.
Have a nice day. If you have
Thank you,
any
sir.
other class, enjoy it. Okay. See you tomorrow then. Bye bye.
Thank you, sir.
Thank you.
Yes, sir.